That's it. All right, today. Oh, no. Oh, this pen again. I thought I threw this away. Shoot. Today's the 9th. And here's what we want to do. It looks like there's like an oversized amoeba on this piece of paper.
Wow, that's gross.
Something like that. I don't know what it is.
Is it on the paper? Or on
Yeah, it's on the paper. It's on the paper. It's like a
I
blob.
don't appreciate that amoeba being.
Whoa.
You have to eliminate that.
Go away. All right.
I'm assuming Tuesday,
I just gotta wave it a little bit.
because that'll be our last meeting with Glad. But I don't know.
Yeah, no, we go fine.
Yeah.
Not to come to the one after.
Okay. We all set? Here's the deal. Here's the problem we have to solve today. We have to solve this problem. Given a vector field or force field, okay, where we're assigning a vector to each point in this plane, and that vector can represent a force. Okay? That's why it's called a force field as well as a vector field. And given some path in this field,
So it is a vector field. We just call it force because it's application space.
well, you know what? In math, they call it vector fields all the time, and in physics, they call them force fields all the time. But they are the same. They're one and the same. What we want to be able to do is, given this path, we want to find the work done in moving a particle along this path from, say, that's from A to B. Okay? That's what we want to be able to do. We want to figure out what is the work done in moving this particle along that path in this vector or force field. Okay? That's what we want to do. So, the thing to do is do what we've done in Calc 1, 2, and 3 all along. Let's take a little piece of this and find the work over that little interval. Take the sum of all the pieces of work throughout that interval. Let the number of pieces go to infinity, get a Riemann sum, and evaluate that with an integral. That's the process. That's what we've been doing. So let's take a point here. Okay. Now, we've got a force at this point. Let's say the force is this. Hey, how you doing? Good. That's good. We've got a force at this point, f of x sub I, y sub I. Okay? Well, we have to find the work done. Okay? Well, work is a force times the distance. Okay? That's what work is. So we're going to take this over a small distance. Let's say delta S. That distance is a small distance along our path. It's a little piece of the arc length. Okay? Well, the only work that you do is the work done in the direction of motion of the force. Okay, either in the direction or the opposite. In other words, if you are moving along a path perpendicular to the force, okay, if you've got gravitational force this way and you're moving this way, there's no work done at all. The work is only done in the direction of the force or in the opposite direction of the force. Okay, not perpendicular. So here's what we need to do. How much of this force is in the direction of motion? Well, let's take a unit tangent vector. At that point. And let's find out how much of the force is directed along that unit tangent vector. Okay? Oh, your seat was taken. That's okay. All right. Okay. So what we're going to do is find out how much of the force is in the direction of motion by finding the magnitude of the projection of this force on our unit tangent vector. This right here. How much of the force is in the direction of motion? Because that's the force we're concerned about. Okay? We're not concerned about the amount of force perpendicular to our motion because there's no work done there. All right, so here's the deal. How do you find the magnitude of the projection of the force on the unit tangent? You remember that formula for the magnitude of the projection?
Dot product over the magnitudes.
Yeah, wow. Dot product over the magnitude of the vector projected upon. That's the magnitude of that projection. Remember what we did to find the projection. We took this, the magnitude of the projection, times the unit vector in the direction, okay, of t.
Oh, that would give you the vector. This would give you the magnitude.
Yeah, this gives you the magnitude. If you multiply by the unit vector in that direction, you get the vector. That's exactly correct. Okay, well, what the heck is the magnitude of our unit vector, t? What's the magnitude of that unit? 1. Yes, it is. Okay, so the amount of force in the direction of motion is that dot product. Okay. What is that piece of work, that little element of work in this interval? It's approximately equal to the force in the direction of motion times the distance, because that's what work is, force times the distance. Okay. What is the total work over the interval? Well, it's approximately equal to the sum of all these pieces of work. Okay. And what is the exact work done on moving the particle along this path? That work is equal to,
How do we know the unit tangent magnitude is 1?
say that again now.
How do we know the tangent magnitude is 1 again?
It's a unit tangent vector.
Oh, okay.
That's it. Because it, by definition, 1. That's equal to the limit, as n goes to infinity, of the sum of all these pieces of work. And what kind of a sum is this? Yeah, we never heard of this before. It's a Riemann sum, but this it's in terms of s, unfortunately. This is equal to the integral, okay, of f dot t ds. It's a line integral over that path. Well, we don't do the line integral. What we do to evaluate a line integral is change it to an integral, a normal, a regular integral, in terms of a parameter t. Okay, so what we're going to do is change this so it's in terms of t. Instead of y equals f of x, we're going to have our path in terms of t, r of t. Okay, so here we go. You ready for this? We're going to change this from a line integral to an integral in terms of t. Okay, so let's do it. So our work is equal to the integral as t goes from, let's say, a to b. Okay, initial point. F, our force, is going to be in terms of the parameter x of t, y of t. T is already in terms of little t, our parameter. That's how we got t back here as in terms of t. But what's t equal to? How do you find the unit tangent vector? What do you do to find a unit tangent vector?
Find the normal and then switch.
Say that again now?
Find the normal and then
That's pretty cool. I'm sorry, I shouldn't laugh at that, but no, because it's pretty cool. Because normally what we usually do is find the tangent vector, which is pretty simple, and then to find the unit normal vector, which is much more difficult, we swap the two and take the opposite of one. We go from here to here. But I want to get to here. How do you get to the unit tangent? What do? We have a position vector r of t. Given r of t, our path, our parameterization of the path, how do we find the unit tangent vector? What do we do? Yes?
R of t divided by the magnitude of R of t.
What'd you say for the numerator?
It's R of t divided by the magnitude of R of t.
No.
Is it R prime?
It's r prime of t divided by the magnitude of r prime of t. It's the velocity divided by the speed. That's how you get the unit tangent vector. You take the derivative of your position divided by the magnitude of that derivative. That gives you the unit tangent vector. The unit tangent vector is your velocity vector made into a unit vector. Okay, is what it is, and it's tangent to the path. What's ds equal to? What's that little element of the arc length equal to? Well, that element of the arc length is equal to, we did this yesterday, that's the square root of x prime of t squared plus y prime of t squared dt. This is what the ds is. That's an element of the arc length. Okay, is everybody okay so far? You guys all right so far? All right, so here's what we have. We have the integral. T goes from A to B, wherever that is. We have our field in terms of T. We have r prime of t divided by the magnitude. Now, see this thing here, this square root of x prime of t squared plus y prime of t squared? What is that equal to? That's equal to the magnitude of r prime. R prime is x prime of t, y prime of t. Okay, that's how you find it. You take the derivative of the x component, the derivative of the y component, to find the derivative of r, okay? And it's the magnitude of that. This quantity right here is the magnitude of r prime. Okay. Check it out. R of t is equal to x of t, y of t. R prime is x prime of t, y prime of t. The magnitude of that is the square root of the sum of the squares of the components. That's exactly what this is. These guys will cancel. We are left with this. The integral from a to b. Now, I don't have to write t anymore. Everything's in terms of t, but I am. X of t, y of t, r prime of t, dt. This is what we're going to use to find the work done in moving a particle in this variable force field or vector field along some path. What it's generally written as, it's generally written this way, f dot dr. Okay? This is shorthand for this up here. In physics, this is the way they usually write it. Do you guys do any of these problems in physics like this? It looks familiar?
That's now we're just jumping into it.
Oh.
What's physics?
All right, here we go. We're going to do some problems. You ready? This is the shorthand way, but this is the way you actually do it in practice. You use this formula here. Let's do some problems. Okay? Let's do, let's find the work done. Let's take an nice, easy path. Let's go from 0, 0 to 1, 1. And let's go in some vector field. Let's say we have the field. Do we want a conservative vector field or not? Let's start off with a conservative vector field. Let's suppose this is yx. What this is doing is assigning a vector to each point in the plane. At 0, 0, we get the 0, 0 vector. At 1, 1, we get the vector 1, 1. And at, let's say, 1/2, this point 1/2, 1/2 along the path, we get the vector 1/2, 1/2. All right, so all the vectors are pointing along the path of motion here. This is a conservative vector field. Let's verify that. Partial of n with respect to x, 1. Partial of m with respect to y is also 1. This is a conservative vector field. Does that make a difference? Well, it doesn't make a difference as far as finding the work done along that path in this field. It does make a difference, however, if we want to take another path. Okay? Let's say we want to take a parabolic path from 0, 0 to 1, 1. Or another path like this, say. This would be y equals x squared, this is y equals x, and this is y equals the square root of x. Those are three different paths to go from 0, 0 to 1, 1. Will it make a difference as to the amount of work that we do? How we get to that point in this conservative vector field? It doesn't make a difference. We should be able to do each of these three problems, three different paths in this conservative vector field, and get the same amount of work. If this were a non-conservative vector field, it would make a difference, the path that we take. We could possibly get three different works. All right? So you ready? Let's do it. You guys psyched or what? Eric, you psyched? Thank you. Okay. All right, let's take the linear path first. Let's go right along y equals x, the most direct path we can take. The work is equal to. Now, what we have to do is get a parameterization of that path. Okay? Parameterization, here, this is the first one. This is along the path y equals x. We need a parameterization of that path. Can somebody give me a parameterization of that path? R of t equals tt. T goes from 0 to 1. Let's do it. All right. We'll go from that. We'll take that path. Let's take a look. The work done is the integral from 0 to 1. T is going from A to B. Our field, our vector field here is yx. But it has to be in terms of t. Where do we get the values for y and x? You take them from the path. This is x, this is y. Okay? X is equal to t, y is equal to t. So our field becomes t, t. Okay? Whatever you have here, you get right from the path. Okay, this is your x component and your y component. Dot. R prime of t. I'm using this formula we developed right here. Okay, that's the formula we developed. R prime of t, well, what's R prime of t? 1, 1 dt. This will give us the work done along that linear path from 0, 0 to 1, 1 in this vector field. 0 to 1, t plus t, take the dot product, okay, it's 2t. Integrate 2t, it's 2t squared over 2. We're going to get 1 unit of work. Joules, we use joules, right? Work units, joules. 1J. For J-nish. Yeah, that's it. Right, yeah, there you go. Nice. Okay.
We got 2 J's.
What's that?
We got 2 J's.
2 J-nishes? Ooh, that's a little, that's one more than really we can tolerate. Yeah.
The other one?
Professor Burns,
Yes.
that second dot product, that's going to be a,
mandatory.
well, at least one of those is going to be just integers, so you're not going to end up with a composite thing, right?
Say again now? What do you want to do?
One of those dot products will end up being just integers, like the 1, 1, so you're just multiplying, or you're just taking the dot product of a vector, you know, with variables, and vector with just numbers, right?
Well, you can get anything in here. You get any kinds of stuff. You can get all kinds of stuff. But hopefully the ones we do, whatever you end up after this dot product, you'll end up with something you can integrate.
I see.
We're going to do another one. Let's do another one. Let's take another path. Number 2. Let's take the path y equals x squared path. I need a parameterization of that path. Can someone give me a parameterization of that path? What?
T squared of t.
Oh, damn it. You are.
What is it?
Oh, T.
T squared. dt squared. You got it. T squared. T is going to go from 0 to 1. Okay? Now, again, like we said yesterday, we have an infinite number of parameterizations of the path. Okay? We have infinite number of parameterizations of our first path, infinite number for our second path. Every one of these are going to be independent of the parameterization of path. As long as you stay on the path, your answers are going to be the same. Okay? Now, for this problem, however, we're taking different paths. It's only because we have a conservative force field or vector field that the work done is independent of the path. Okay? So let's see what happens when we use this path. The work is equal to the integral from 0 to 1. Now, what's our field? It's yx. This is x, this is y. So our field now is y, t squared, x is t, dot, r prime, which is 1, 2t. You take the derivative of each, okay, dt. So now check it out. Make sure you check this out.
Is that the other way around? 2T, comma 1?
Let's see. We got, here's our r prime is 1,
No.
okay, and 2t. Take the derivatives of each of these. Don't take the derivatives of this. Take the derivatives of this. This is r prime right up here. Take the dot product. T squared plus 2t squared. Oh my. We're going to get 3t squared. Oh, this is going to be different. Obviously, if you integrate t squared from 0 to 1, you're going to get a different answer than if you integrate 3t squared from 0 to 1. But let's see what happens, okay? So, how much room do I got? Do you guys still see that? Yes. Okay. Integrate 3t squared to get 3t cubed over 3. The 3's will cancel. You get t cubed from 0 to 1. And what do we get? 1J. 1J. Yeah. Yeah, 1J. Same thing. As long as it's conservative, we don't care what path we take. Let's do another path. Let's take the square root path over the top. We're going to come up from above. You ready?
Let's do go from 0 to 2.
0 to 2. And this same one right here?
Get 2.
Well, you're going to end up up here somewhere, and you're going to totally different work. But if you can make it so that your path from 0 to 1 goes along here and ends up at the right place, yeah, it'll give you the same amount of work.
The square, one square, never mind.
You could do it. You could do it instead of t.
Functions that y equals 1 and 1, same point.
Yeah, you have to start at the same point, end at the same point, and follow the path. Now, can you make a parameterization so 0 to 2? Yes, you can do it. As a matter of fact, it'll probably be t over 2, t squared over 4, and that will do it. You could do it. Yes?
So why is it t squared t for your vector function inside the integral, and then it's dt squared for your RT?
For this here, I needed to go along this parabolic path, which is y equals x squared, and I had to start at 0, 0, and I had to end at 1, 1. So by setting up this parameterization, t squared, I go along that parabola, y equals t squared, y equals x squared, because the y is the square of x. And if I start at 0, I'm going to start at 0, 0, and when I go to 1, I'll end up at 1, 1. I have to start at the right spot, end at the right spot, and stay on the path.
So I'm just wondering, is there a reason why you switched it to t squared t inside the integral?
Inside the integral here, yes, because my force field is yx. And that said, take the y component and then take the x component. And that's what I did. I had to switch it. Okay, that was my field.
Use the force.
Yeah, I used the force. That's right. Okay, let's take another path. Okay, let's take the square root path. Okay, here we go. Number 3. We'll take y, this is the path, y equals the square root of x. I need a parameterization of this path, okay, that will get me, go ahead. What do you want to do? What's my parameterization? T, square root of t. T goes from 0 to 1. Okay. Now we could be more creative here. We could do a 2t here and a square root of 2t here and go from 0 to 1/2. That would work. Would you rather do that and we'll change it up some? Or does it make any difference? All right, let's do the easiest one. This is the easiest one along this path. So what's the work here? Integral, 0 to 1. My field is yx. Yx. R prime is 1. Now the derivative of this is 1/2 t to the negative 1/2. Oh man, this is not good. This is not good at all. So the work is the integral from 0 to 1 square root of t plus 1/2 square root of t. When you do this dot product, you get the 1/2 this times this. Okay, so I end up with 0 to 1, 3/2 square root of t. Okay? That's equal to, let's do the integral, t to the 3/2 divided by 3/2. The 3/2 will cancel. I'll get t to the 3/2 from 0 to 1, which is equal to 1 joule of work. It doesn't matter what path we take. Not only that, this is unbelievable. Not only that, we could take any path we wanted to. We could go along the x-axis and up. This is what we're going to do tomorrow, actually. We're going to go around a rectangular path and calculate the work done and going this, and this to get back to here. Now, if it's a conservative vector field, what will that work be? 0. It will be 0 if you end up where you start. But if it's a non-conservative field, that work may not be 0. Okay? And we're going to divide it up in those 4 pieces. But there's more to it. Because it is conservative, we know that this is the gradient to some potential function. And if we can find the potential function, there's a totally different way of finding the work done. Let's do it. Now,
Really quick, so couldn't we just have just as easily have done t squared and t? Why did we have to?
t squared t. I could have done that. Yeah, that would have worked. That would have worked. T squared t would work because that would be where the y is the square root of x, and that would have worked. That would have done it. Could have done that. We could have done any of these things as long as we start at the right place, end at the right place, and travel along the path. But here's what I also want to show you. Because it is conservative, we can find its potential function, okay? F of xy, for which this vector field, okay, this vector field is its gradient. So how do you find the potential function? Well, you find the potential function by integrating the x component with respect to x. What's the integral of y with respect to x? Yx or xy. And what's the integral of x with respect to y? Same thing. Our potential function is xy. Okay? Here's our field. We said it's conservative, meaning what? It has a potential function. How do you find the potential? You find the potential by integrating the y with respect to x. We did this yesterday, it seems to me. Okay. What's that?
2 days ago.
Oh, 2 days ago? I don't know. Sometime. We did it sometime. And this is xy. And we reconcile the two by coming up with the function xy. Okay? This is its potential, okay, or potential function. How else can you find work? You can find work in a conservative vector field by simply taking the difference in potential, end minus start. So you take the potential at your end point minus the potential at the start point to find the work done. F of 1, 1 is 1. F of 0, 0 is 0. You end up with 1 joule of work. In a conservative vector field, the difference in potential is the work done. It doesn't matter what path you take. Okay? How's that look? That's cool. All right, you guys ready to do one? Let's try another one. Let's do this one. Let's say we get a... I'm going to give you another conservative one, okay? So you can find the potential and do it that way. I want you to verify that. So here we go. Let's take the field. Let's take a pretty simple field here. How about 2 y? There's a conservative field. I want you to find the work going from, let's start at 0, 0, and let's go to 10, 1. Okay. Here's what I want you to do. 2 things. 1, find the work along the linear path. Find the work by finding the difference in potential. Go ahead, and then I'll do it. Then we'll do it together. So you guys do it first, though. Give it a shot. We have one more topic to cover, one more way of finding work done along a closed path in a non-conservative vector field. That's with Green's theorem, and that's the last thing we'll do. We'll do that tomorrow. And we're essentially done. Wow. Good stuff. Z also said it's better to take the diffie cubes and linear here, 2 separate courses, than to go up to UMass and take that 1 3-credit course, because he said in 3 credits, they don't teach you much except just what you need to do a very specific set of problems. So he said it's better, you're better off taking them here. But the other 2, how'd you miss the other 2? They're fall courses, those other 2. The CSC ones, and not spring courses.
I don't know. The first week was too bad. I was in trouble with like figuring out plus.
Yeah. Oh wait, was I?
No.
Yikes.
Where?
You got a number? You got an answer? How are we doing? You got an answer?
Yeah.
What'd you get?
19.5 joules.
90 and a half. 19 and a half. Oh, I just got 20 and a half. But I did it in my head. You got 20 and a half? Eric and I agree? That's it. It's 20 and a half.
Wait, ran out.
All right.
Oh, man.
Oh, it's plus. No, it is 20.5. You're right.
Cool.
What did I do wrong?
Uh-oh.
I got 50.5.
Yeah, that's what I did.
What'd you get? People got different answers?
50.5.
So,
50 and a half, Dylan?
so finding the linear path is another way of saying finding the work.
Not another way. They're not really equivalent. Find the linear path is the path you're taking. Then you got to find the work in moving that particle along that path. That's what the work is. How much work is done to move that particle along that path? And in a conservative vector field, which is what you have, it wouldn't matter even what the path you took. You could take any path, as long as you get from 0, 0 to 10, 0. You could go onto the third quadrant first and then head up there, and you could find the work done, and it would all be the same 20 and 1/2 joules of work. Okay? No matter what path you take. You guys ready? Let's do it. We'll do the linear path. First of all, I need a linear path parameterization. And y in terms of x is y is 1/10 x. Okay? But we need it in terms of t. We need a parameterization of the path. So, does somebody have a parameterization of that path? T and t over 10. And t goes from 0 to 10. Now, you could do 10t and t, and have t go from 0 to 1, and that would work, and that would be fine, okay? But, I don't know, you could do it this way too. Doesn't matter. Okay, so let's do it. Once we have that, let's do the problem. The problem is to find the work, 0 to 10. The field is 2y. Well, 2 doesn't change, but the y is t over 10. Remember, your path gives you the x and y components that you're going to use for your field to set up the parameterization of the field. The y is t over 10. Okay? It's 2y, and here's y. Dot r prime, 1/10 dt. That's equal to 0 to 10. 2 plus t over 100. Okay? dt. That's equal to 2t plus t squared over 2, t squared over 200. Whoa. From 0 to 10. That's equal to 20 plus 10 squared, 100, 1/2, minus 0, minus 0. It's 20 and 1/2, or 41/2 joules of work. Okay. That's using the linear path. Let's take the difference in potential. To find the difference in potential, we'll have to find the potential function first. Our potential function, f of xy, is, what do? Well, you integrate the x component with respect to x, and you get 2x, plus some constant in terms of y. Let's do it. Okay. So it's 2x plus some constant, possibly in terms of y. What else can we, how else can we express our potential function? Well, integrate the y component with respect to y to get y squared over 2 plus a constant in terms of x. We got to reconcile the two and come up with one function that satisfies both requirements. That function is 2x plus y squared over 2. Okay, it's got both all the requirements. What do we do to find the work done in going from here to here? Find the potential at the end. Okay, that's 2 times 10 plus y squared over 2. That's 20 and a half. Find the potential at the beginning, which is 0, and take the difference in potential. And the difference in potential, the work done is 20 and 1/2 joules of work. Okay? Bless you.
Thank you.
Are you allergic to work? Is that it?
I might be, I don't know.
That is that.
I sense that being a freebie question on the exam.
Oh, I'm going to give you the exam. This exam is it's a breeze. This is a possible test question.
Oh, man.
Yeah, this is a top of, what?
This is the drop test.
Oh, man, maybe I better change the test. Yeah, I think I'll change it. I'll make it easier or something. All right. We got one more thing to do. But tomorrow what we'll do, you got to find the work done around a rectangular path and add up all the works. And then what we have Green's theorem, which enables us to find the work done in a non-conservative vector field around a closed path. Pretty cool. It's good stuff. And we're going to do that tomorrow. And we'll be done. See ya. Oh. Dylan.
Confused. The way, like,
Wait a second.